All right. Hello, everyone. Today I'm here with Sherlock Huang, who is newly joined here at Meta. And this is an interesting new format that I wanted to do. Basically, Sherlock is going to ask me questions about things in PyTorch from a sort of newcomer's eye. Although, Sherlock, you're not really a newbie because you've been working on Onyx runtime for quite some time before coming over here. And I'm going to answer them, and we'll see how this goes. And today's episode also has a video component with it because there are some diagrams that we're going to reference as we're going. All right, Sherlock. So do you want to get us started?
Yeah, thank you, Edward, for inviting me here. Yeah, so today's we're probably going to focus on the dispatcher component. So as I was reading your blog, so I come to this impression that originally dispatcher was designed to handle mostly just the device type and data type dispatching. So over time, it grew into this big magnetic and central place for many, many features. So like, can you tell me a little bit about the history of how we come to this stage and a little bit of the history about the dispatcher?
Sure. So your guess about where the dispatcher used to be implemented is right. So in the beginning, in the way beginning, we had Torch. It was for Lua Torch. It was written entirely in C, and essentially all we had like separate copy pasted files, one for CPU float tensor, one for CPU double tensor, one for CUDA float tensor, one for CUDA double tensor. And then there was just some bindings to the Lua programming language that actually like figured out where you would go so you didn't have to like write individually which operation you wanted to do. So this got ported to PyTorch. And so the first version in PyTorch, there was some binding layer in Python that once again basically knew how to get to the right implementation. And when Zachary DeVito rewrote our bindings so that we had a C++ library intermediating between Python and the Torch C libraries. Before, it was like directly to C and was very hard to understand. The original thing that we needed was simply, to dispatch on the device type and then to dispatch on the D type. So there was a virtual method that we used to do the device dispatch, and there were a bunch of macros for basically letting you stamp out multiple copies of each implementation for D types. So since then, we've added tons and tons of more features to this dispatcher, and there's a more recent diagram talking about dispatch keys, and the model we have now in C++ is that there's an order of various operations that we can do in the dispatcher, and we basically run things in order depending on whether or not they're applicable to some computation or not. So like in this example, autograd is in red, and that's because autograd is a very common layer people want to do. So you hit autograd and then you do CPU. So autograd was like one of the first layers to get added afterwards, and then all of these other ones sort of got added over time. Did that answer the question? I guess I didn't answer this question you had over here, which is how to like think about VMAP, but at least autograd, that's where it lives. It lives here. By the way,
Yeah,
Torch dispatch, it's like a backend. So there's just a Python key over here, and that's how Torch dispatch gets handled in the backend section of the dispatch.
yeah, that answers the question. So like it seems to me that like the order of the dispatch key is extremely important. So as we add so many features, so how do we determine the order of the dispatching key? Like, is there any principle behind, making the deciding the order?
This is a great question. So the order is indeed important. And in fact, there is not a single well defined order necessarily in all cases. For example, FuncTorch, which is the new library for doing Jack style transforms on PyTorch, it provides two levels of functionality, VMAP and AutoGrad, and you can actually have them ordered one way or the other, and these correspond to different but both useful operations. One of them computes per sample gradients, whereas the other one is like normal. You have a batch computation inside of AutoGrad. So that's kind of troublesome, and like some of the more recent work has been about like sort of getting us away from this fixed set. But the order that is in C++, and this order is kind of important because it's the one we can efficiently implement, this order is basically sort of worked out based on like what the average use case in PyTorch is. So, for example, one like there's a question about tracing versus autograd. So why is the tracer before or after autograd? Well, actually, the tracer key is this interesting legacy concept for torch script tracing. And we've been talking about this new thing called AOT autograd, which knows how to trace autograd, and that's implemented using the Python key. The Python key is after autograd, so indeed you get the traced forward and backwards in this situation. Another example is autocast and autograd. Autocast is before autograd. Why is that the case? Well, it's because if you do a bunch of casting, you need to also know how to differentiate through a cast to lower or higher precision. So autocast doesn't handle that. It just inserts the new operations, and then autograd handles it. So there's a lot of thinking about like what you want the semantics to be, and the ordering of the dispatch keys is like our best guess about what you want in this situation. And hopefully it is useful, but sometimes it's not.
Yeah, this is great. So I also heard about in terms of dispatch key, there are two categories. There are like backend related dispatch key, and then there's another feature keys. And backend keys is always the end destination of the dispatching, right?
That's right. Well, almost, because the Python key, which we treat as a backend, can in fact start executing other PyTorch code, which will go through the dispatcher again. It's a sort of re-entrant mode of execution. But most normal backend keys don't do that. They just actually do the compute.
So let's say like user want to specifically override the dispatching order. Is there any way that a user currently can do that?
That's also a good question. So in the C++ dispatcher, there's a fixed order, and that's it. You're out of luck if you want to reorder things. So how does functorch do it? How does functorch? Let's see. Do I have batched? Yeah, I have in this picture. Batched is before autograd. So that's the order you get when you use PyTorch only. So how does functorch let users reorder it? So the basic idea is that you have an inner tensor and you have an outer tensor. And each of these tensors gets its own copy of the dispatch tree. And then what you do is you say, okay, on the outer tensor, skip batched and go to autograd. Cool. You do your autogrady stuff. And then you go to the backend key. It's going to be the Python key, or in functorch's case, there's a special key that they've got for like going back to the front. And this goes to the inner tensor. It goes back to the beginning, and then you this time hit batched, and then finally you get to the true backend. So you basically like if it's not in the right order, you just stack as many of these as you need, sort of nulling out all the things you don't care about. And all of these layers are optional. You don't have to do them if the functionality isn't relevant.
Yeah, this is the same idea, similar idea as the tensor subclassing, right? So when you wrap tensor over tensor over tensor, you automatically get multiple stacks of this dispatch key, and then you can compose them in any way that you wish.
That's right. So with tensor subclasses, so functorch's implementation is done in C++, but with tensor subclasses, you can do it entirely in Python simply by having a tensor subclass that contains another tensor on the inside. And we actually have an example of how to do that this way in subclass zoo. It's in the functorch.py file.
Yeah. So I want to dive a little bit into this backend select key. So in the diagram, it seems that okay, we do a bitwise OR on all the hardware keys, uh, but the one that end up being selected is the leftmost of the dispatch key, right? But in reality, like a single operation can only run on a single device. So like basically the multi-dispatch behavior doesn't apply to the backend select. Is that the right understanding?
Sort of. Okay, so there are a few things going on here. So this multi-select is for handling multiple dispatch where you like have a CPU tensor added to a CUDA tensor, and this figures out, hey, you want to go to the CUDA key, not the CPU key in that case. Backend select is for a different situation, which is when you don't have any dispatch keys in the inputs in question. So backend select is used primarily for factory functions which don't take any tensors as inputs. And because they don't take tensors as inputs, there's no tensor input dispatch keys to get you to the CPU or CUDA factory function that you need. Indeed, you would instead have to look at the device argument to figure out which one you want. But we didn't write any like special logic, which is like, oh, if your argument is a device, then I know how to extract a dispatch key from it. Instead, we just said, well, we'll just put you in this backend select kernel. It will go and look at the arguments, figure out what to do, and then eventually take you to the correct kernel.
I see. So for, let's say there's a binary op, and one input has a set of dispatch keys, say batching and tracing, but on the other input, it can have another set of um, dispatch behavior. So when we plug these two inputs into this binary op, so you're saying that both, it will take a union of this dispatch key and invoke every single feature that both of them have, right?
Yeah, that's right. And then the implementations of the feature, like batched or autograd, would be responsible for knowing how to deal with a tensor input that quote unquote wasn't batched or wasn't autograded. In JAX, we call this lifting. You have to lift a tensor that doesn't have that functionality into the world of autograd or batching.
I see. I see. So it seems to me that like okay, the destination is always on this backend device selection part. So has there been any consideration on,
Mm-hmm.
for example, breaking this one joint dispatcher into multiple ones, especially for example for the backend ones, because it's always the destination. It doesn't seem to be mixing with other orders. Yeah,
With the layers. This is a great idea, and in fact, we have done that. So Brian Hirsch recently landed a PR that gives us a lot more dispatch key space, and the way that he does it is by treating backends specially, so they don't. You can sort of have something that is both AutoCast and AutoGrad and XLA, but you can't have something that's both XLA and CUDA. So he encodes those differently. With it's still one in 64, so we didn't actually separate them, and the dispatch table is still sort of set up as one table, but morally now we are treating backends differently than the layers in question.
I see. Is there any other like category concept in this dispatch key? For example, like we have this multiple autograph dispatch key. We have this view and conjugate and negative view. So it seems to me like the dispatch key is not like completely flattened. There are structure within it, but somehow it's all just appears to be flattened. So is there any consideration to put them in a more structured way?
Oh, that's a good question. So for the layers, I actually don't think there is more structure, except in the sense that you might want to reorder them arbitrarily, which is what PyTorch is about. So my general way of thinking about every layer keys. So backend keys are terminal, right? They don't ever call anything else. Layer keys can call into other layer keys, and we sort of normally go down the dispatch key chain as we get there. So the way I think about a layer key is it's basically a rewrite of some Torch API operation, some A10 operation into some smaller A10 operations, right? And you continuously like desugar the A10 ops into more and more A10 ops until you finally got in the backend, and then those are the actual operations that you need to run. So in that sense, there isn't really any meaningful grouping, right? And any transformation from a single A10 op into several A10 ops is a valid transformation. And we might group them up because some of the transformations do similar things, are implemented in a similar way, like conjugate and negative. Those are very similar. But you know, like you don't need to you don't need to bunch them up from the perspective of dispatch because they do want to be ordered in this way because that tells you what order the transformations happen. I guess there is an interesting point here to be made, which is whether or not sometimes transformations are commutative with each other, but we don't encode this logic in any way right now.
So another mystery that seems to me is like all this new feature end up landed in the dispatcher. So is it by design or is it uh, just part of the constraint that we end up in the dispatcher? So like if you look back into all this feature that was added to this dispatcher, is there any particular ones that could have lived outside the dispatcher or done in a different way that but eventually somehow still got into the dispatcher?
That's a good question. So let's be a little concrete for a moment. So let's say, for example, um, let's talk about AutoCast for a moment. So AutoCast was an interesting feature. It wasn't even developed by folks at Facebook. Michael Carilli over at NVIDIA had implemented AutoCast as some. I don't even remember how he. I think he was like monkey patching the PyTorch source code and basically doing a lot of work to like basically automatically insert casts to lower precision, without having to modify your program. And so I think we were at the PyTorch Dev Day, and I heard what Michael was doing, and I was like, hey, you don't have to do it this way. We've got this thing called a dispatcher, and in particular, something you can do in the dispatcher is you can write what's called a fallback kernel. So this is a single polymorphic kernel that like will operate on all of your operators. So you can just write one of these fallback kernels. Actually, I think for AutoCast, it's a fall through kernel. It just ignores the execution if it's not an operator that knows how to do casting. And other than that, it was just a very convenient way to insert functionality into PyTorch, interpose it, without having to like do stuff like monkey patching. Now, today in 2022, we've been adding a lot of new features that let stuff happen in Python userland. For example, I've got a PR, a torch function mode, which I'll be landing soon, which basically lets you do this kind of interposition at the Python API level. And this can't happen in C++ because once you've got into C++, we have only the like narrow C++ set of types. So all Python objects have gone away. We've translated them into C++. But sometimes you want to like do some operations in Python, and that's why torch function modes are kind of like dispatcher layers, except they're living at the Python level. And then you probably could have implemented AutoCast in Python, and you would only do it in C++ because you had a speed concern or you needed to work with the C++ front end or something like that. So yeah, it's a really good question. And so I guess historically the answer is there wasn't a good way to do things other than in the dispatcher. But we are now adding more hooks like Python dispatch and like torch function mode, which lets you do these in userland.
Yeah, yeah, thank you, Edward. That's all the question I have for today.
Okay, thank you, Sherlock, for asking some great questions. Talk to you next time.
Thank you. Bye bye.